So let's look at the first question here. So you have snack food fried in coconut oil had soapy flavor. Why would that be? That means you have just an off flavor, yes.
Is it because of lactic acid?
Is it what?
Is it something like lactic acid?
Lauric acid. Yeah, but what caused lauric acid or any other, let's say, free fatty acids? There we go. So you have obtained free fatty acid during frying in an oil multiple times, and due to heat, moisture, and then the oil unsaturated, then you get, not necessarily unsaturated, but you just get hydrolysis of fatty triglycerides into fatty acids. You could also measure oxidation, just in case to see if oxidation will occur as well. So you can do peroxide value, or TBA, or T-bars, thiobarbituric acid reactive substances, which a test used to measure secondary metabolites. So the second problem, you have the fried snack food stored in a warehouse, and it has a painty fish flavor, an off flavor. Why might this happen? Yeah.
Oxidation.
In this case, it was most likely oxidation. So if you have, if they're packed and the packages are permeable to oxygen, and you have the warehouse temperature went up for some reason, it's hot environment, then you would wind up having oxidative acidity. There are multiple methods to measure them. So you can say, in this case, you can do primary peroxides, you can do secondary, like N-acetylene value or T-bars. You can also do hexanal measurements. So there are multiple tests. Always safe to put primary oxidation product test as well as secondary oxidation product. So the third problem, you had a cereal product made with raw wheat bran, and it had off flavors. So what would be in a raw wheat bran? Enzymes. So you most likely will have lipases. So you will most likely have free fatty acids. And you would also have lipoxygenases. So you have lipases and lipoxygenases. Lipases will cause hydrolytic rancidity. Lipoxygenases will promote oxidation. So we test for both free fatty acids, for hydrolytic rancidity and peroxide value, and another test, hexanal or T-bars, for oxidation. Yeah?
For oxidative rancidity, are the off flavors due to the volatile oxidation product?
Yes.
Okay.
Yeah.
And those are like aldehydes?
Aldehydes, like malonaldehydes,
Okay.
like hexanal, pentanol. Okay, so this one, this fourth problem, we had it in the first lecture in food analysis as an example. So we had a cereal pellet that was sold by a supplier to a producer, and the producer would fry this pellet, make it into a snack, and package it. So they complained that the finished product was rancid. So you had to go in and investigate. So is it your pellet that started started to be rancid or something else that happened later on. So what might be the reasons for the problem? What would you be thinking about?
Frying oil.
So you want to collect sample of their frying oil, that one thing. And then what else will you want to check? Yeah.
Permeability of their packaging.
The permeability of their packaging. So you would check their packaged product, the permeability for oxygen, and then you will test the product in the package. So you will test your pallet, you test your oil, you test the permeability of the package, and then you test the final product. Okay. All right. You have developed a new butter containing fish oil. So fish oil is highly polyunsaturated. So before placing the product on the market, you need to determine its shelf life. How would you do that? Any idea? We do an accelerated shelf life study. So we have 3 tests that you can choose from. The oven test, where you would just put the sample at 60 degrees Celsius over an extended period of time, and then you will pull samples out and measure peroxide value so that you can determine the induction period. You can also do an oxygen bump test. So that's when you put your sample in a chamber, and the chamber you pressurize it with oxygen and you put the whole thing in boiling water. Then you would measure the drop of pressure due to the uptake of oxygen, and that would be induction period. The last one is the oil index test, where you just put the oil at a high temperature, 130, 140, you bubble air into the oil, and then the volatiles are driven to another flask with water, and you measure conductivity. The volatiles will start coming once oxidation happens, like formic acid will start forming, for example, and become volatile, and then conductivity of the water will change. So any one of those you can pick. You don't have to list those 3 tests. Pick the one that you're comfortable with as long as you explain it well. And you mentioned that you take out a sample and you measure peroxide value to determine the induction period. Okay, so the last one. So here you work in a quality control for a company that makes peanut butter. So you received information that between certain period of time you have certain lots of peanut butter that may have been improperly stored, and you are concerned about potential lipid oxidation in the product. You have a total of 50 lots. So what tests do we do? So stored improperly, then you're suspecting oxidative rancidity. So you can first, it's 50 lots, so you're not going to measure them all. So you want to say that you will randomly select representative samples of the lot and test them for certain oxidation products. So you can do primary oxidation products and secondary oxidation products, and you specify a test. You can say you'll do sensory evaluation as well. And then based on the results, you would decide if you reject all the lots or you let them go. Okay, any questions about this characterization sheets? You had it.
Yeah, so for part B, for that last question, is oxidative rancidity dangerous? So if you detect any, would you have to not?
If you, depending on if you have oxidized cholesterol and non-aldehyde, certain level, yes, become toxic. But the idea is also flavor. So if you have off flavor, that's a quality issue. You don't want to send it out. It's not just toxicity, it's also the quality in terms of perception of the consumers. Okay. So before I start going through the review questions, as many as we can, do you have anything you'd like us to discuss? Any topic you would like to go back to? No? You understand the material perfectly well? Okay. Alright. So let's look at the review questions. Do you have them in front of you or should I pull them out? Where are they? Okay, I can't find them. I'll pull them from Moodle. Alright, this should have said you received 140 pounds bags. I should correct that. Every year I say I want to correct that and I don't. Okay, so you received 100. Please make sure that it is corrected that way. So you are using whole wheat flour as an ingredient in a baked product. Upon receiving the flour from the supplier, the quality control lab is responsible to withdraw samples and carry out proximate analysis. So you receive 140 pounds bags of flour at a time. State your sampling plan and size you would choose. Explain your answer. So if you have 140 pounds bags, are you going to test all of them? No. So what would you usually do if you want to randomize?
You could just do the random number generator and that in each bag that's randomly chosen tested in different ways.
Okay, so first of all, we give the all in bags numbers, but how many bags do we test? You're thinking of AOAC, you're thinking official for nutrition label. Yeah, if that's the case, you take 12. If it's not, you take the root number, the square root. So 100 bags, you would select 10 out of 100 bags. So if we say quality control, it's different than nutrition label. If we say nutrition label, you definitely want to get 12 bags and then take 6 replicates and then do composite sample. That means you combine them and then you take samples for application. That would have been if we said nutrition label. So that's good to bring that up. If we say quality control, you don't have to go by what FDA states or USDA states. Okay, so it would be the square root of 100, you take a 10, and then you follow the procedure for taking samples from a bag. So you would go diagonal and take one from one corner, a sample from one corner, and another sample from the opposite corner. That should be enough, 2 samples per bag. So what you want to say in this though, briefly number the bags, take 10, and sample 2 samples from each bag. Yeah.
So when you say state the sampling plan, that's not like a quick, this is the sampling plan, like you mean actually just explain the sampling plan.
Yeah, explain the sampling.
There's
Yeah,
no
because-
like name for the sampling plan.
Well, randomized sample selection.
So should we say that?
Yeah, you can say randomized sample selection, and then you would explain that, because you're asked for the size that you would choose. The size is not the amount. What I meant is by size is the number of samples you would pick. Okay? So then you would say, I number the bags, and then take the square root, select the 10, and etc.
Ma'am,
Yeah.
so in our notes, we went over like single, double, multiple sampling. In what instances would we use those rather than just like throwing it out?
So the single, double, and well, you can use that. You can state it as well in order to reject. But here you're just dealing with 100 bags. If you have 1,000 bags, and then you cannot, the square root of that will be a lot. So you would then just randomly select single, double, and multiple, and then look at number of defects. So it really has to do with your starting amount. Are you looking at 1 factory day production? Are you looking at 3 factories and 1 week of production? Okay. Now, you solve it on your own as a practice. Do you have any questions about that? It's just basically using the data to generate the different concentrations. Okay, so you're given all the different weights, and then you just need to know what you're looking for. So if you're given a thimble plus sample, then what do? You want to subtract the thimble plus the extracted sample, you get the weight of the fat. So make sure that you know what you're looking for so that you know what you want to subtract what from. So I'm not going to go over this calculation. Just do it on your own, and if you have questions, let me know.
I do have a question real quick.
Yeah,
Sorry, you do want us to know conversion factors, right, from nitrogen to protein? You want us to memorize those?
Okay, so I did give you those in the last exam,
Yeah.
so I will just give it to you.
Okay.
If it's not here in this question, just, what is this, flour? So it would be 5.7 for flour.
Okay.
For wheat. Okay, so C, to determine iron content, would you use the ash obtained from dry ashing, or would you rather follow a wet ashing procedure?
I'd say dry because it's not volatile.
Iron is volatile.
In the bags and that.
Yes. So iron is volatile. So if I ask you about iron, it would be, and if you're interested in measuring iron content, you'd rather go with wet ashing procedure so that you prevent volatilization during the dry ashing that could happen. So you want to say, because iron is volatile, we'd rather to go with wet ashing, which will maintain iron in solution and prevent any losses due to volatilization. So state an official method for analyzing each of the mentioned constituents. It's always easy to select something we've done in the lab. So instead of selecting hydrometer for moisture, for example, which we didn't do in the lab, you could say vacuumometer, or you can say convection oven, or you can say Carl Fisher, as long as you explain it briefly, but with this, briefly, but with the important information. So if you say convection oven, so you would say you put it at 100 degrees overnight and then measure weight difference. So it's a gravimetric procedure. So that would be simple. If you choose, let's say, Soxhlet for fat, make sure you mention that it's a semi-continuous. You would use petroleum ether, and the sample would get soaked in the ether and for 4 or 6 to 8 hours. After that, you take the difference in weight between the original sample and the extracted sample, and you get the fat content. So you mentioned the solvent, that it's a semi-continuous, and the weight difference would be the fat. If you choose Mujiner, you want to make sure that you include the digestion step with HCl, because it's flour. If it were cheese, and I was finally finishing up all the proximate analysis lab report, and I saw, and also in the exam, I saw that some of you put digestion with base. It's not really digestion for the cheese. You know, the cheese is a curd. The protein formed coagulant. So the ammonium hydroxide solubilizes the protein to release the fat from the matrix. So HCl digestion, base solubilization. So make sure you know the difference between the two. If you select Mujiner, since it's sweet, you want to say digestion with HCl followed by extraction with two ethers, the PET ether and the ethyl ether, and then evaporation of the solvent. Then the weight, you measure directly the weight of the fat, which is different than Soxhlet, where the Soxhlet is the difference in weight is the fat. In Mujiner, you weigh the fat directly in that pan. So if you choose protein, DUMAS, for example, it's good to say it's a nitrogen combustion. Sample is combusted at high temperature, 900 degrees, and then NO2 gets scrubbed and produces N2 gas, and that is measured by thermal conductivity. And then you use a conversion factor. So there's key words that you want to say that describe the method. You don't have to say the weight of the sample, for example, or the calibration of the instrument. You don't have to mention that. If you say Teldar, for example, some of you are very brief. I do say briefly, but some of you get really brief, and they say digestion, distillation, and titration. Well, yeah, but digestion with H2SO4 to fix nitrogen into ammonium sulfate. You have to use the key words. And then neutralization with NOH to produce ammonia, which gets distilled into boric acid to form borate, which gets titrated with HCl. And then number of equivalents will be used in German amount of nitrogen. And then conversion factor. For iron, for ash, it's the muffle furnace, very simple. You combust the sample at high temperature, 500 degrees C, and then you weigh the residue, which would be the ash. Iron, you would want to describe the atomic absorption for that. So you would use an iron-specific lamp, and the sample will be solubilized in acid, and then aspirated, gets atomized, absorb light, and then you get you convert absorption into concentration using standards. Any questions about that? Okay. So for wheat, corn breakfast cereal, you want to measure different carbohydrate components. So when I say what preparative steps you need, is you want to start with select a representative sample, you homogenize, homogenization is important, and then defat and dry, or dry and defat. These are your steps. And then importance of drying and defatting, not to interfere with the carbohydrate extraction and measure. Okay, what would you use to measure total starch? How do we measure total starch? No? Nobody's gonna tell me? No. You mean the H-protein method? No, that's for total carbohydrate and beverages. You don't do that for starch. So starch, you want to hydrolyze it all the way to glucose, and then you would measure glucose by the coupled enzymatic reaction. So first of all, how would you hydrolyze starch? So you would use alpha amylase, and then you would use glucoamylase to break down the dextrins that are formed by alpha amylase, break them down to monomers, to glucose. And then you can select one of the two reactions I gave you for glucose. One that is simple is glucose oxidase, and then coupled with peroxidase. And then you would get measure absorption, you'll have a calibration curve using glucose, and then you convert back to starch. When I say show the chemical reaction, I don't necessarily ask you to draw. So you would just put glucose in the presence of glucose oxidase and oxygen. It will give you the peroxide, and then the other product from the glucose. And then the peroxide is reacted with peroxidase, and then you would get a measurement. Let me pull that up. So here, gluconolactone, so you don't have to write the structures. And then here, you don't have to memorize, just say reduced dye, and then the peroxide will oxidize the dye to get you a color. So you don't have to memorize the name of the dye. How would you measure the total dietary fiber, soluble fiber, insoluble fiber? Again, you would just have a brief layout of this. The digestion with the alpha amylase and protease and glucoamylase, and then you filter. You all know that because many of you answered the bonus question like that, which wasn't the correct answer. Okay. So, as means of examining olive oil, where is it? No, here. So state the principle of the method used to determine saponification value and show the chemical reaction. So with the chemical reaction, I don't really mean write it all out. So it will be triglycerides plus 3-KOH that will give you water and 3K fatty acids. So that would be your chemical reaction reading. And then when I say state the principle, that means, okay, so your oil is saponified with KOH. And then you want to state the unit. So it's milligram of KOH that saponifies to 1 gram of fat. Okay. It's what? Oh. Duh. It's glycerol. I knew I did something wrong. Okay. And then when we saponify with KOH, to continue, you would titrate the remaining KOH with HCl to calculate the saponification value. Okay, so now how do we calculate the saponification value? So basically it's at neutralization, so NV equals NV, and we derived this equation in class, so it's basically, well, it's right there. So you would need to apply this equation. Remember that it's milligrams per 1 gram. So that's why, because it's milligrams per 1 gram, you don't divide by 1,000, you don't convert milliliters, to liters, so there's no division by 1,000, and because it's in 1 gram, so there's no multiplication by 100. So if you remember the unit, you will remember the components of your equation. And 56.1 is the molecular weight of KOH. So basically, what you have to answer this question, you have 48 or 45 milliliter for the blank. And in this case, it's blank minus sample because you add KOH in excess. Some of the KOH will react with your triglyceride and the remaining you titrate. So if there is no fat, that means it's blank, all the KOH will be present, so the volume of the blank will be high. So it's volume of the blank minus volume of the sample, which is 5.8, and then you multiply by the normality of HCl, which is 0.1, and then you multiply by the molecular weight, which is 56.1, and then you divide by the weight of the sample, which was 1.024, and that's it. And then you would get 214.76. Okay. So was your value within the range stated? It wasn't. So what does it mean? If not, what conclusions can be made? So your range is 184 to 196, and then you got 214.76. So it wasn't. What does this tell you about the oil? So it didn't fall under the specification.
Does that mean it might have been some hydrolytic rancidity already?
No. Adulterated by an oil with higher molecular weight triglycerides or lower molecular weight triglycerides? Lower. Because you have the higher saponification value is correlated with lower molecular weight. So the next question asks you about calculate the average molecular weight of the main fatty acid in the oil, assuming that the saponification value was 1/9. In order to do that, okay, so you want to remember your equation. So it's triglyceride plus 3KOH will give you glycerol plus 3 fatty acids. That's the first equation you want to remember. And also there is this equation, triglycerides plus 3H2O will give you 3 fatty acids plus glycerol. This is for the molecular weight. This is the actual equation of the saponification. So if the saponification value is 190 milligram, that means it's 0.190 grams saponifies 1 gram of fat. That's the definition, that's the units. So it's 0.19 gram that saponifies 1 gram of triglycerides. So if I want to know the molecular weight of triglycerides, so 1 mole is reacting with 3 moles. 1 mole is equivalent to how much, what is the molecular weight of 1 mole of triglyceride? This is what I'm looking for. And 3 moles of KOH is 3 times 56.1. So each mole is 56.1 grams. So 3 moles is 3 times 56. So we have 1 mole reacting with 3 moles and 0.19 grams saponified 1 gram. So I use this equation, 3 times 56.1 times 1 over 0.19. And I get, what do I get? 884. Okay, so this is the molecular weight of triglyceride. Now they're asking me for the fatty acid, average fatty acid. So I use this. So this is really the molecular weight of triglycerides plus 3 times the molecular weight of water equals 3 fatty acids plus the molecular weight of glycerol. Usually I should give you the glycerol molecular weight. If I didn't, I will do in the final. It's 92. So basically you have the triglycerides is 884 plus 3 times 18 equals 3 fatty acids plus 92. Three times 18 is 54, so you have 884 plus 54 minus 92 over 3 equals 1 fatty acid molecular weight. So that would be 282, and that is the molecular weight of oleic acid. If you intend to hydrogenate the olive oil, not the corn oil, we're talking about corn oil. Do you have questions about this calculation? Yeah. So if you intend to hydrogenate the olive oil, would you measure iodine value again after hydrogenation? Why? And would you measure trans fat content and why? Do you measure iodine value? Yes. Why? Because it is a measure of degree of unsaturation. So I measured it before and I measured it after to determine the completion of hydrogenation. And trans fat can be produced during hydrogenation, especially incomplete hydrogenation. So it has to be measured given its health adverse effects. So if you need to measure degree of oxidation, which methods would you use? Name at least 3 and explain the principle. So we talked about several already with the fat characterization. So you can say peroxide value, T-bars, anisidine, or peroxide value, anisidine, and hexanol. So you can pick any 3 of what we talked about and provide a principle for each. All right, let's think about this together. Instead of me just spitting it out. So I gave you 3 different properties of the proteins. I gave you size, I gave you the size, gave you the isoelectric point, and I gave you the net charge. So when I want to separate the protein from a mixture, and I have 3 different characteristics, in order to purify, I would do 3 different separation or isolation methods. So I gave you size, I can do what with the size? Which separation? Size exclusion chromatography. Okay. I gave you isoelectric point, pH. So pH precipitation. So I would just, after I get the 18 or around 18 kilodalton, there will be a couple of them that have similar molecular weights. So I would get that fraction, and then I would bring the pH down to the isoelectric point of 5.2, centrifuge, discard the supernatant, take the precipitate. Now I have a precipitate of not necessarily just my protein. There are a couple of proteins that will have similar isoelectric point. So now I have precipitate. I will just take that, solubilize it again, and then run anion exchange chromatography. the order doesn't really matter. You can start with whatever you want to start with, size exclusion or pH precipitation or anion exchange, as long as you show these 3 different ones based on what's given in the question. Okay. If you want to quantify this protein after isolation using an immunoassay technique, indicate the type of assay you would choose and explain its principle. So I'm asking for an immunoassay and it's a protein. What do you think a logical one would be? Talk about it in class. Sandwich ELISA. In sandwich ELISA, because it's a protein, so you will have multiple epitopes. So one antibody can capture and another antibody can use for detection. So it would sandwich the antigen. And then you would explain its principle. So you will have a capture antibody that has been immobilized on a plate. Then your sample, you would put your sample with the protein in it. The protein will bind. And then you will put another indicator antibody that is labeled with an enzyme. And then you add a substrate, and then you measure the absorption of the product. So if you want to determine your recovery, that means how much protein you were able to isolate, what method of analysis would you use to measure protein content in your isolated fraction? So your isolated fraction should be a purified protein. So, and it will be in solution. So think about research methods in this case. Now if you put Dumas and Kilda, it's not a wrong answer. You can still put those, but in isolated fractions you can do simply a 280 measurement. Your absorption is at 280. You would measure absorption at 280 and you have a standard curve with bovine serum albumin, and then you convert absorption to concentration. It's very simple. Or you can do the Bradford assay that you've done in the lab. You react your Bradford assay with the protein, you get the colored compound, you measure absorption, you have a standard curve. Or you can do BCA, bisinthonic acid assay. So you can do any of the methods that are research methods on a purified fraction. Okay, so you want to identify GMO in a soybean field where you don't really have a lab. And we didn't get to that part in lecture, but you can actually do a strip, which is called lateral flow test strip, instead of doing a full-blown analytical technique in a lab. So what constituents you would be analyzing? We're looking for GMO, so it's usually a unique protein that we're looking for. And then the lateral flow strip would be your immunoassay that you would use. And we'll go over its principle today in lecture. And it's basically based on sandwich ELISA. And we'll also in class we'll go over Western blot, and it's not possible to do Western blot on the field just because it is a highly sophisticated method that requires elaborate technique and a lab. And then we'll go over the principle of it in class, so you would explain its principle here. Question 6, it really focuses on the next lecture, which is the contaminants of concern. But this is a very typical question that I would ask, is I would give you either a list of products, or I would give you a list of contaminants. And I ask you which products these contaminants might be in. So for example, here in milk, what residue do you think is of concern that we usually want to make sure we measure and it's not there? Those of you that did cheese and used milk. Antibiotics. So antibiotics, talk about this in class, but antibiotics is one contaminant or residue that you don't want to have in milk. Wheat kernel, usually it's extraneous matter or insect larvae that you would watch out for. And again, we'll talk about that in the last lecture, the extraneous matter. Peanuts, what would be a contaminant or a substance you don't want there? Aflatoxins. So a mycotoxin, specifically aflatoxin. Green vegetables or any crops really? Huh? Pesticide. Bottled water, this you might not know, but it is a common concern. It's bisphenol A, and we'll talk about that in class. Deep fried potato chips. You have sugars, and you have asparagine, and you get acrylamide. Again, all of this will be covered in class, but these are the main ones that would be in each of these products. So let's look at the question. So the question says, identify one chemical or matter you will be analyzing. And I say matter because it could be extraneous matter. It could be insect part or insect larva. It could be stones, or it could be glass, or it could be whatever. So you would identify, that's what we just did. State the method of analysis and explain its principle. Indicate means of detection. So a lot of these could be an immunoassay. It could be an HPLC-MS method, like pesticides. Milk, the antibiotics is a charm test. It's an immunoassay. So for each one of those, you would state the method and very briefly describe its principle. Okay? And then it's very important to state the means of detection. So I say indicate means of detection. So is the detection going to be mass spectrometry? Is detection going to be absorption? Is the detection microscopy? Like many times you come under the microscope for extraneous matter. So you have to end your method with the detection. How did you detect it? Here's another typical question. You want to measure vitamin C. What did we do in the lab? Basically, the endophenol. So when I say put the reaction, again, don't draw the structure, just the name. So you have the oxidized form of endophenol, and then you have the L-ascorbic acid that would reduce it, and you will get a reduced dye that is colorless. So as long as you put L-ascorbic acid plus oxidized endophenol will give you a reduced dye and an oxidized aldehyde-ascorbic acid is what you get really. What would you do to determine the amount of aldehyde-ascorbic acid? We talked about mild oxidation of vitamin C will give you aldehyde-ascorbic acid, and it's still viable. It's still biologically available. And if it's already there in your sample and you want to capture it, what would you do? What would we do? Aldehyde-ascorbic acid is the oxidized form of L-ascorbic acid. Add a reducing agent. So I would add a reducing agent at the beginning, and then I had in the class somebody asked me, well, if you add a reducing agent, it's going to reduce the dye as well. No, we add a small amount of reducing agent, and we run a blank of that reducing agent, so that the difference would be only the reduction due to L-ascorbic acid. What alternative method would you use to determine both forms of ascorbic acid? Alternative method. We talked about the fluorometric method. And in this method, you actually oxidize all L-ascorbic acid to aldehyde-ascorbic acid. So the aldehyde-ascorbic acid would be the one that you get, you react it with the fluorescence and you measure the fluorescence. In this case, you're measuring both forms because you oxidize everything and then you do the reaction. And then what are the precautions that you need to make while preparing your sample for analysis? What we did in the lab, we had an acid solution that we added. So low pH prevents the oxidation or reduces the rate of oxidation of L-ascorbic acid. So we don't want to expose it to a lot of oxygen, so we monitor the pH, that means we use acid to lower the pH. We prevent exposure to oxygen, light, and heat. So let's say you want to determine the vitamin C in the frozen concentrate, you do not thaw the concentrate in boiling water. Okay? So you just want to make sure that you do not expose the sample to anything that would induce oxidation and result in underestimation of the vitamins. To measure the titratable acidity of a fizzy orange juice, you need to prepare standard solution of 0.1 normal mH. That's what we did in the lab. If you haven't noticed already, the lab is an integral part of this course. So whatever we did in the lab will help you, if you go over them and review them, will help you with this, with the exams, obviously, and the final. How would you prepare 0.1 normal NOH from 50% NOH stock? So who wants to do that for us? Nobody. So you have 50% NOH. What do we do with that? You want to do it? Yeah. Why not? Just a little bit of an exercise. You can erase what's on.
Is it 50% weight by volume?
Yeah?
Okay.
You want to explain what you're doing?
Oh, yeah, sorry. So,
Here you go. You're the teaching now.
so to do the conversion, you do the normality times the volume equals normality times volume. That's what you eventually want. So you're starting, in order to determine the normality of the starting NaOH stock, you multiply 50% weight by volume times or you divide it by the molecular weight using this calculation to determine the moles per liter. And that's your normality because it is not like one of those where it has multiple equivalents per whatever. Anyway, and then you multiply, so you have that value, and you're looking for this value, and you want it to equal 0.1 moles per liter. And then you would have the
1 liter, you're preparing
1 liter. Okay. And you would solve for this value.
Yep. Okay. So let's get the numbers. So when you have 50%, that means 50 grams in 100 milliliter. You want to convert that to a liter. So that would be 500 grams in 1 liter. Okay? So 500 grams in 1 liter, you want to convert that to molarity, really, and molarity equals normality because you have 1 OH. So you want to convert this concentration, grams per liter, to molarity. So in order to do that, you get the number of moles, which is the mass over molecular weight. Now you have the mass per liter, right? So you have the mass, you get the molecular weight. The molecular weight of NaOH, I would usually give you, I didn't here, but what's the molecular weight of sodium? 23, O16H1, so the molecular weight of NaOH is 40. Okay, so then you would have here number of moles equal mass, which we just got, over the molecular weight, which is 40. So that gives you, what, 12.5? Yeah? That's 12.5 moles. And since now we have it in a liter, then this would be the molarity equals 12.5 moles per liter. So, which is equal to normality. So we have here the 12.5 times the volume that we want, 0.1 times liter, which is 1,000 milliliters. And then we solve for the volume. So this is 100 over 12.5 is 8?
Yeah.
Yeah. So the volume is 8 milliliters. And then you would finish that. You prepare 8 milliliters. You take 8 milliliters and you put it in a 1 liter volumetric flask, make it up to volume with water. So you get that. And why do you need, and then how would you standardize it? And this was the missing information in the question on the quiz. So the student did not state how they standardize it. That was the question. So you needed to say that NaOH is standardized by the standard acid, and what we used in the lab was potassium acid phthalate. So you would standardize it. That means you titrate the standard acid with NaOH, and then at the point of equivalent with an indicator, which is phenolphthalein indicator, you would have N by V equals N by V, and you solve for the normality of NaOH. That's how you state, how you standardize the NaOH solution. Why do we need to standardize the NaOH solution? Why do we care about that? Well, simply because it's used in the equation of calculating percent titratable acidity, or the percent acid.
How come, so we make a solution of NaOH and then we have to standardize it. How come we don't care about standardizing the potassium?
Well, it is a standard, it's called a standardized acid, it's a powder. and you weigh the exact amount that is you're told. And
So, but there's like still errors in that process.
yeah, there is still error, but you do your best you can. Yeah. But if you don't standardize your NUH, you will get more error because that's what you're using in the calculations. So there's always experimental error. There's no way around it. Okay. And this question B is the same one as you got in the quiz. You just calculate percent acid. So in this case, you have citric acid. And somewhere in the question, I would give you a hint towards how many pKa's you have. And that's when you need to convert to the equivalent weight. And that's what you have in your equation. You need the equivalent weight. So I will give you the molecular weight of citric acid. And somewhere I say citric acid has 3 carboxyl groups. So 3 carboxyl groups, that means it can donate 3 hydrogens. So the equivalent weight is 192 divided by 3. So in the equation, you have to include that. So your equation, it's the same equation that we've all been using, which is the equivalence equation, which you have the normality, which let's say standardize it and it's 0.1 normal NUH, and then you have 20.5 milliliter that you've used to titrate. Milliliter, that's normal. And then you multiply by equivalent weight, which is 192 by 3. I believe that's 64. And then you correct from milliliter to liter, so there's 1,000. And you divide by the volume of the sample because you're getting a percentage of the sample. Grams per milliliter is what you're getting. And you multiply by 100 grams per 100 milliliters. So it's weight by volume. Okay? So you get a percent of citric acid, which is, I don't know. I have not calculated that. Maybe I did. 0.67%. Citric acid. Here's a typical question. You forgot to boil the sample prior to titration. Is your value over or underestimated? Explain your answer. So you forgot to boil. So what do you have in your sample? CO2 you have, okay. So when you say you have CO2, what does CO2 convert to in water? Carbonic acid. So it's very important to say, okay, so it's not boiled. You have carbonic acid, the CO2 in there, the CO2 is going to convert to carbonic acid. And another piece that is very important is we say carbonic acid buffers at pH 8.2, which is the end point. So because it buffers, you're over-titrating. And because you're over-titrating, you're overestimating. So there are keywords then that we're looking for. CO2, carbonic acid, buffers at 8.2, and then you overshoot, over-titrate. And then draw the titration curve. We've done that in the quiz. And there were a couple of common mistakes in the quiz. Is what are we plotting? We are plotting pH against milliliter of 0.1 normal NUH. So we're plotting pH. So your x-axis is milliliter of NaOH. Your y-axis is pH. When you have 3 pKa's, assuming that the pH of your juice was under 3.06, you will see the buffering zone of the first pKa. Okay? If we want to assume that we started at 2, for example, then you're going to see 3 buffering zones. So to be safe, draw 3 buffering zones. Okay, so let's say we started here, 2. So I would go, I'm titrating, I go up, I see a buffering zone around 3.06, and then I titrate, I see buffering zone at 4.74. So it would be good to have them listed on the y-axis. And then go up, and another buffering zone at 5.4. And then continues to go up, and then I see a sudden increase, and that's pH 8.2, and that's your milliliter, which was in this case 20.5 milliliters. So this would be a complete graph that you would graph. You have 20.5 milliliter, you need to show that you did that at pH 8.2. And then 3 pKa's, pKa1, pKa2, pKa3. That's a complete figure. Number 9 is another exercise for calculating proximate values, and in this case it's cheese sample. And I ask you to calculate each constituent that needs to appear on the nutrition label on dry and wet basis. That means I'm asking for protein, fat, and carbohydrate. Right? Total carbohydrate. When I say each constituent appearing on the nutrition label. So that means you have to calculate the ash as well, the moisture, the fat, the protein, and subtract from 100. And then you'll get the carbohydrate. And then you use the equation from dry to wet and wet to dry. So for fat analysis, it's cheese. So you will have a dry basis value. The ash will be on dry basis. I don't necessarily tell you that. Well, I do. Weight of simple but plus dry sample. I do give you that hint. Anyway, so just remember that cheese of using subset will be on dry basis, ash will be on dry basis, you convert those to wet basis, the others you convert to dry. You have wet, you convert to dry. So you just keep that in mind, don't forget when you're solving similar samples. Are the percentages reasonable? So, you just estimate. Look at the percentages and estimate. If a cheese sample, what would be the protein, and carbohydrate should be minimal, moisture, it could be anywhere between 10 to 50% depending on the cheese sample that you have. What are the minerals that need to appear on the nutrition label? As of now, the nutrition label does not have potassium. It is the recommended, the approved, but they didn't do it yet. So the minerals that would appear would be, of the current one, what? Iron. What else? What's on-
Sodium.
Huh?
Sodium?
Sodium, and then one more?
Calcium.
Calcium. Okay. Explain the principle, the method, and you go back to the AA method. If you want to explain ICP, you're welcome to do that as well. All right, this number 10 is a buffer. Would you like me to go over buffer preparation again, or? It's the same example we gave in class. I can work it out with you if you like. Yes, no, ICDS. Yes? Okay, let's do that. So, the easy way that I would do it, there are multiple ways to approach preparing buffer. The easy way I do it is I prepare my acid and my salt solution at same concentration that I want my final buffer concentration. That's my starting point. If I have the same concentration that I want to end up with, then I'm only trying to solve for the volume. How much of acid and how much of salt I want to mix together to get a buffer of that concentration. So that's the first thing you want to think of, is I want to prepare my acid solution, I want to prepare my salt solution. And what's the final concentration? The final concentration that I want, 1 molar. So I want 1 molar, and I'm starting with 3 molar phosphoric acid and 3 molar sodium phosphate stock solution. So it's very easy. In this case, I will apply M by V equals N by V for each one of them. And I'm starting with 3 molar, solving for volume. I want 1 molar and I want 1 liter of that. Or, let's just go. That's molar, molar. Okay, and then my volume, this will cancel, and then my volume is 1,000 milliliter over 3. So that would be 333.33 ml. So for both of them, since I have 3 molar stock solution for both, then for both of them, I take 333 milliliter point 33, and then I make up to 1 liter with distilled water. So now I have both 1 molar solution. Then I apply your Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of conjugate base over concentration of your acid, the non-conjugate, the associated acid that has the H. Okay, so I plug in my values. So I want to prepare pH 7 and the pKa of phosphoric acid is 6.86. So I want to get the volume, the parts. So one part of this and a part of that will give you a whole, right? So that's why I would do A minus over 1 minus A minus, because the whole, right? You can put it 100, you can put that a liter, you can do it whatever you want. So you can actually, if you want to get the volume of 1,000 milliliters, so you can directly put it here as 1,000. Then you'll get the final amount of A minus in milliliters. And the difference would be for the AH. Okay, so I don't have a calculator with log. So what would be, so 7 minus 6.86, so you have 0.14 equal log A minus over 1,000. So what would that ratio be? Anybody got it? Well, if you don't want to get it back, you have it? Huh?
1.38.
1.38. So if we have 1.38 times 1,000 minus 1.38 A minus. So I just substituted, okay? So this value equal 1.38. So I bring this over, 1.38 times 1,000 minus 1.38 equals A minus. I bring that over, so you have 1,380, 2.38 A minus. So 1,380 divided by 2.38,
580.
huh?
580.
580?
Yep.
Then AH would be 420. 1,000 minus 580. So I would mix 580 milliliter with 420 milliliters of the acid. 580 milliliter of the salt with 420 milliliter of the acid, I will get pH 7 buffer. Okay. So you are investigating a case of natural juice adulteration, where artificial flavors have been added with no declaration on the label. Flavor profiling is first thing you want to do. So flavor, volatile, flavor present in very small concentrations. So do I go for GC or HPLC? I go for GC because they were looking at volatiles, first of all. Second, GC is much more sensitive than HPLC, and you have much better resolution given the length of the column of the GC versus the length of the column in HPLC. So if you have volatiles, GC is the first place to go. So that would be your answer. So I would use GC over HPLC because of the small concentration, the high sensitivity that is, the volatility and the better resolution in this case. My battery is running low. Okay. So what detector? When I ask for a detector, what would be the easiest thing you want to do or select? Something we've done in the lab. It's always an easy thing to do, to say. You can say a quadrupole, that's what we used in the lab, and make sure you explain it. Or you can say ion trap, I don't care, as long as you explain the principle correctly. Or you can use, say, MS. MS is a detector, so you can link GC to MS and get identification as well as quantification. Actually, one of the next question asks about, where did I put that? Oh, is there one over there? That's interesting. Sorry. Oh, well, C asked you if you did not see, you saw peaks that you didn't have standards for. So in this case, I asked specifically for MS. So the first one, you have to say ion trap or quadruple or triple quad. So you have to select a regular analyzer. Oh my God, look what I've done.